Welcome back, Wolfpack. Today's lesson is 10.3 and 4 coordinate proofs using distance with segments and using distance with quadrilaterals. Our essential question continues to be, how can you determine the similarities and differences between various quadrilaterals? And today's content objective is that you're going to be able to prove quadrilaterals using the distance formula and the Pythagorean theorem. So as I mentioned earlier in class, we're not going to do a lot on this video because I want to do more of it in class, but I do want you to be familiar with some of the things that we are going to be going over with, okay? Nice little review. First up, the distance formula. You have to know the distance formula. You need this, you need this, you need this. I cannot emphasize it enough. Please be memorizing it. The distance formula, the distance between 2 points. The square root of x squared minus the square root of x2 minus x1 squared plus y2 minus y1 squared. Secondly, the Pythagorean theorem is a squared plus b squared equals c squared. And the Pythagorean theorem is for when we have right triangles, okay? And if we are looking for the length of something on a coordinate plane, we can use the Pythagorean theorem often instead of the distance formula, okay? But we have to have the picture on a coordinate plane. So, first up, example number 1. Square ABCD has vertices at A, 2, -3, B, -2, -1, C, 0, 3, and D, 4, 1. What is the length of a side of a square? So, I would highly suggest just drawing a picture just to be familiar with what you're looking at, A, B, C, D, okay? And it wants to know the length of a side of a square, and it doesn't obviously matter which side because in a square, all sides are equal, okay? So, I'm just going to find the length of AB. So I'm going to find the length of A and the length of B. So this is going to be my x1, y1, and this is going to be my x2, y2. And I will need to use the distance formula because I do not have a picture on a coordinate grid. So -2 minus 2 squared plus -1 minus -3 squared. Square root of all of that, and then just simply solve. -4 squared plus -1 plus 3 is 2 squared. The square root of 16 plus 4, the square root of 20, and you can plug that into your calculator and find it in a decimal form. Or I know that the square root of 20 is equal to the square root of 4 times the square root of 5. Well, the square root of 4 is 2, so 2 square root of 5. That's the best answer for this, 2 square root of 5. Or if you put it into a calculator, that's fine as well. So the length of any side of the square is 2 square root of 5. I found AB, so that means all of the sides are 2 square root of 5. Example number 2, determine the most precise name for the quadrilateral with vertices at A is at 0, -1, so here's A. B is at 1, 4, C is at 4, 3, and D is at -3, 2. So what's the most, obviously I'm not drawing this perfectly, but you get the point. The most precise name for that. Well, in our last class we talked a lot about, I'll try to do it a little bit nicer. We talked a lot about finding the slopes of lines. So hopefully you are still very comfortable with that. Looking at the shape, it looks to me to maybe be a rectangle. But before we can figure that out, we'll see if it's even a parallelogram. And parallel lines, a parallelogram has to have 2 sets of parallel lines. So we're going to find the slope of AB, and we need to compare it to the slope of DC. So the slope of AB is starting at A, 1, 2, 3, 4, 5, a rise of 5, and a run of 1. And the slope of DC starts in here, 1, 2, 3, 4, 5, and a run of 1 as well. So are those lines parallel? Yes, they are. So we have our first set of parallel lines. Now let's compare BC to AD. So slope BC, slope AD. Remember, we need to go to the right. So down 1, 1, 2, 3, negative 1 over 3. And AD is down 1 over 1, 2, 3. Are those two lines parallel? Yes, they are. Okay. So obviously you can see the picture. So they have a picture on a coordinate grid, then obviously it's on a square. I know I tell you all the time you can't just judge what you see based off the picture, but since we actually have a coordinate grid, I can kind of tell that it really cannot be a square. But it could still be a rectangle. And we talked in last class that a rectangle needs to have right angles. Well, in order for it to have right angles, that means the two lines that form the angle have to be perpendicular. So, BC and AB, are they perpendicular? What's the slope of BC and what's the slope of AB? The slope of BC, right here, is negative 1/3. And the slope of AB, right here, is 5 over 1. Are those opposite reciprocals of each other? No, they're not. Okay, so these are not perpendicular. And I can even test it by multiplying them. Negative 1/3 times 5 over 1. Negative 1 over 3 times 5 over 1 equals negative 5 over 3, which is not negative 1. So again, they are not perpendicular. So since they're not perpendicular, this means that there are not right angles, it's not a square, it's not a rectangle, and we can tell looking at it that the sides are not the same size because it's on a coordinate grid. So the best name for this then is just simply parallelogram. We cannot give it anything more specific than parallelogram because it doesn't have right angles or equal sides. So parallelogram. Okay. Again, this is the exact same thing we did in last class. Just another example of it, and that's where we're going to stop because I want to do the rest of this in class. But when we are naming quadrilaterals, we are looking to see, do they have parallel sides first? And we look at that by checking the slopes. Do they have right angles? Again, check the slopes. So we're looking at the slopes of the line for a lot of what we're doing. Hope this makes sense. Thank you for having it done. I'll see you next class. Have a great day, Wolfpack.